Hey everyone, finally got a haircut and we're here with a Div 2 contest today. Alright, so we'll be getting started in a couple seconds. Yep. Okay, grid, select a black cell. Okay. Oh, I see. Okay, so it's either 0, 1, or 2, or impossible. Okay, if that's not what I want. That's not what I want at all. Okay, there we go. So if same, we're gonna print 1. If any, we're gonna print 2. Also gonna print -1. All right. And submit. Do you want to do B or C? Maybe C looks. Oh, let's do C. Why not? Prime tree. What's that? Every path consisting of 1 or 2 edges is prime. What? How can you do that? Because otherwise, because usually you get odd. Okay, so you're gonna use a lot of 2s, right? Okay, I think it has to be a line. Like you cannot have this. You can't have a degree 3 node. If you have a degree 3 node, yeah, then you have problems. So it has to be a line. Okay, it has to be a line, and then we're just gonna alternate 2 and 3. All right, so what's the output format? Ah, oh, it's kind of annoying. Okay. Okay, so what we're going to do is auto or adjacency of the node. If nay is not a parent, edge color node nay node equals color. And we're going to self nay node 5 minus color. I'm going to call this with, and then oh, it's just give it E actually. I mean, I don't have to do this, but let's just do it. All right, first solve of C. Maybe I picked the wrong problem. Anyway, let's keep going. Okay, Manhattan distance, K buckets, K seats, 1 bucket paints 1 seat. Oh, that's funny. Oh, I see. I think Tina just blocks off the middle seats. Although, wait, what? So, I think you just sort everyone by their distance to the 4 corners. So, and then you just output this array. Is that right? Okay, let's do it. All right, now to problem D. Okay, find 2 integers where the GC is not present. Oh, okay. So a number needs two numbers that are multiple, that are not a multiple of something else. I think this is some Mobius function stuff. Do you have a lot of solos, maybe? So this should be okay, and yeah, so a particular number it's a Mobius function. Okay, so I think what you do is count we need this. All right, and then the number of pairs. Or just if multiple count of 2, then you have a problem. Yeah. Okay, so maybe I don't need this multiple. If present a continue. Now what we want is if multiple count A equals multiple count A times B, then that is true. Is that it? You don't even need this Mobius stuff then. Oh, it's a multiple count. Okay, never mind. Never mind this. Cool. All right. BCD. Let's see. I want to do E first. Go up. Okay, you want to reach the top. Okay, so this is just the shortest path problem, but you have these weird edges. Rn. Oh, actually, n times m is pretty big. So I think we have to. Oh, okay. I think we just have to throw out things that aren't one of the relevant points. So you have a lot of ladders that get to the floor, and then a lot of ladders that leave the floor, and then you can do like a per floor Dijkstra. That would work. Do you need to do that? The other thing you do is you that's kind of hard. Maybe this per floor texture is let me think about this a little bit. So you have to solve that problem. So I think you, yeah, I think you do. That's fine. I think you do a per 4 Dijkstra. I mean, it is just this line graph. There's relevant, and then there's all right. And then we also have map from int to int64 dist. All right, we're gonna Dijkstra this 4. I didn't even read the ladders, did I? Alright, so n letters A, B, C, D, H. You can have ladders from the same point, can't you? No, there's K ladders. A, B, C, D, H. So what do we want to do? Ladders A, B, C, D, H, and then relevant A dot insert B. Okay. That's how many columns we have, and then we're going to do yep. Okay, so All right, and then we're gonna have a priority queue. Priority queue is going to take, it's gonna be min heap. In place dist for call. Right. Okay, so right. So no columns for call. We can find an index. If index is greater than 0, we can go left. We can go right. D plus x times gap. If nd is less than dist floor, what is this? No, this is x floor. This logic is almost the same. We're going to do this. We're going to subtract in this direction. We're still going to have that. We're still going to have that. Yep. Okay. Now we're going to do the ladders on this level. Oh. Alright, if dist floor call, this is the new floor, plus, actually, minus health is less than dist new floor, new column. Actually, just call me mice. Ugh. That's it. Is that it? I think that's it. What happened? What? Oh, I didn't need to make it. Dude. Wait. Oh, yeah, okay. Yeah, that's right. Oh, I just missed the minute. I assume geothermal's done. Nope. Hit on node. Alright, let's make sure we can overflow. I don't need to do this anymore. Alright, I guess doing Dijkstra on the floor was good. What's the time limit? 2 seconds. That seems fine. Alright. One last problem. K is even. Okay, yeah. Pieces. Wait, what? Each pair? Oh, you're given a bunch of pairs. Translation, rotation, flexion. Flexion? Okay. How do you do that? Does this mean subsequence? It means subsequence. Is even. Take that line down the middle. Do they give you repeats? Oh, they do give you repeats. So it's actually weighted. What? Okay, apparently this problem is doable in 16 minutes. Okay. So it is weighted, unfortunately. You can take that line down the middle, you can take this line down the middle. You can take some sort of zigzag. Like this. Why does a zigzag work? Does it just have to be rotationally symmetric around the center? What about the reflection thing? How would you get the reflection thing then? I don't think you can get the reflection thing. I think you get the rotation thing. Should I be able to do this? I mean, this edge, this cutting this cost this much. And you're just taking shortest path, essentially. 0, 0, 0, 0. Is that what it is? I don't think reflection comes into play. It has to just be that rotation. I think this is what you want. Reflection doesn't make sense, and then... Alright, yeah, you know what, let's do it. It's another texture problem that is a bit funny. Okay, so... It's actually a keys problem. It's a it's always a square too. Okay, we're gonna just set this up basically. We're gonna read the end things. And then, yep, and then how do you do this step? Wait, so there's like this, which actually looks like this is 1, 3, this, and 1, do that. There's this, which actually looks like this, and then look at that. So R1++, C1++. That's what you're doing. You're adding to the cost of Yeah, and then afterward we're going to do that is the transform. Yeah, so okay. I just want this function. Actually, I want this function. I want this too. Okay, so it's actually n minus best. All right. 8, 7. It was just okay. So code does that. Yeah. Cost. Are these? Oh. These are one indexed. Yeah, these are one indexed. Oh, that might have just fixed it. Okay. Okay, that's good. Nice. Does this make sense? I mean, it's fast enough. And then, do I have overflow issues anywhere? I don't think so. I should have made a get cost. All right. Let's see. Anyway, good stuff. Gonna grab some food and then be back in a bit to explain. All right, back now, and let's talk about these problems. So I'm not going to explain the problems. Feel free to check out the link below to look at them, but just going to talk about my approaches for each. Okay, so for problem A, for this one, if there's at least one black cell anywhere, you can always do it in 2 operations. You just fill out the entire row, and then you find the black cell in that row that's in the right column, and then you fill out that entire column. And you can move from any cell to another cell in that way. So the answer is always at most 2. If we want to draw it, we could do that with so for example, let's say we have this and we need to get this cell to be black. We can fill out this row with 1 operation, then we can pick this one, and we can fill out this column. So that's 2 operations. So that's the idea. And then really we need to figure out, is the answer 0, 1, or 2, or is it impossible? It's only impossible if there are no black cells at all. So that's our -1 case. And then the 0 case is also pretty simple. It's 0 when the cell is already black. And then the 1 case is also pretty simple. It's 1 when there's another cell in the row or column that is black. So we just need to check all those things. That's what my code does. So read this in, check if it's already black. If so, it's 0. And then this is a Boolean for same row or column. This is another Boolean for is there any black. We just check all of the black cells. If we have the same row or column, we set same to true. And then we always set any to true. So same is 1, any is 2, and then otherwise it's -1. Yep, that's problem A. All right, problem B. Oh yeah, so problem B involves Rahul choosing a seat to try to be as close to Tina as possible, and then Tina chooses a seat to be as far from Rahul as possible. And Tina can block K seats from Rahul. So this is, I guess, another grid problem. The main idea is for any particular seat, the farthest seat from it will be one of the 4 corners. And in fact, Tina should actually just pick the K seats that have the closest farthest corners. So in other words, for every cell, we're going to say that its worst distance is its distance to the farthest corner. And then Tina should pick the K cells and block them when they have the lowest worst distances. So we're just going to compute that, put that into a list. So for cell RC, the distance is max of R and n-1 minus R plus max of C and m-1 minus C. And yeah, we're just going to sort that and output that. And that solves each of the K from 0 through nm-1. Because, yeah, like I said, Tina just blocks the cells in their order of worst distance. All right, that's B. We'll just move along quickly here. Problem C. Yeah, okay, so problem C. So the first idea is that you can't have anything that has 3 or more neighbors. And the reason for that is, well, actually, it's a precursor to that. Basically, anything with at least 2 neighbors, one of the edges is going to have to be 2 in particular. And the reason for that is, let's say we're not using 2, then both of these are going to be odd primes, right? For example, 3 and 5. And then the problem is that 3 plus 5 is even, so it cannot be prime. And yeah, basically the sum of every 1 or 2 edges is prime. And so at least one of these is going to have to be 2. And 2 works as long as you find a twin prime for the other side. So yeah, if any node has 2 or more edges incident to it, at least one of them has to be 2. And then no node can have 3 edges, because here, well, if we just think about this edge and this edge, one of them is going to have to be 2, and one of them is going to have to be, an odd number, right? And then what does that leave us for this edge? Well, for this edge, we're in trouble, because we can't put an odd number, because that would not add up with 5 to make a prime. But we also can't put 2, because 2 plus 2 is going to be 4, which is not a prime. So yeah, in fact, you just cannot have a node with degree 3 or more. Everything has to have degree 2 or less. And then because this is a tree, the only trees that have everything with degree 2 or less are just the paths, like the straight line trees. So the only way to make this work is that the tree we're given has to be a straight line. And yeah, I mean, that's just what we're going to check here. Check the degree of everything. And then once we do that, we have a straight line, and we need to color the straight line. And this part was a little bit annoying. I just did a DFS. I found a leaf and did a DFS. And then all you have to do is, what I did is just alternate 2s and 3s. Because that way, every month 2 path will have a sum of 5, which is good. Yeah, and then it takes a bit of DFS to work out the edge colors, and then you have to print the colors in the order that they came in, which is all a little bit annoying, but it's not too bad. All right, so that's C. Let's move on to D. Okay, yeah, so D. So for D, the key thing is that the number is only up to 10 to the 6th. And basically the key logic in here is that for any number A, if A is not already there, you can get A if and only if there are 2 numbers bigger than A where their GCD is A. So basically the way that I do this is I just count the multiples, the number of multiples of each number. And obviously for a number A to have 2 bigger numbers that have a GCD of A, it has to have at least 2 multiples. And then those multiples cannot have, a divisor, a common divisor that is something bigger than A. So the way that I check this actually is that, so A is possible if the multiple count for A is at least 2, and for every multiple of A, B, like for every multiple B of A, there has to be some multiple of A that is not divisible by B. The way you check that is the multiple count of A has to be bigger than the multiple count of B. So that's really the key idea here. So if this is true, multiple count of A equals multiple count of B, that means that every multiple A is also divisible by B, so we have a problem. And if that's not true for any B, then we do have 2 numbers that are that have a GCD of A, and then we're good. So that's basically all I'm doing here. It is A log A time, where A is the max AI, 10 to the 6th. And so that's pretty efficient, and that takes care of the problem. All right, moving right along. The funny thing with E and F was I solved both of them with Dijkstra. So for E, yeah, we have these ladders, we have these, we also have ways to move across the floors, but we take like damage from moving across the floors. And we want to have the shortest path from 1, 1 to N, N. And basically, the nice thing here is that you can only take ladders up, you cannot go back down. So aside from the left-right movement, there are no cycles. And basically what I end up doing is it's kind of a modified shortest path algorithm where between floors it's like a simple, it's more like a DP, but on the same floor it is, I do a Dijkstra. Because basically that's kind of the easiest way to handle, oh, I have all these points that arrive, that can arrive to this floor at this location with this health cost and I want to find the cheapest cost to leave from a certain column on that floor. And that's what I'm doing Dijkstra for. So it's really just a bunch of taking care of the input values, and then you have to be careful because n times m is too big. So I only take care of the relevant columns for each floor. And then, yeah, you just do a Dijkstra on the floor, and you start with the starting distances for each of the columns, and then do Dijkstra. When you pop something, you look at the two neighbors. So there's the column just to the left of it, and there's a column just to the right of it, and you add those two neighbors in if you improve them. And then after that, you take all of the ladders from this floor and try using that to improve future floors. And then once you're done, you just check the distance at the end, and yeah, you're good. So the code is a little long, but it's fairly straightforward code if you've done Dijkstra before. All of this is just like relatively standard Dijkstra. This is the neighbor iteration, and so on. No, I do not want to open my document writer. Okay, so that's E. One tricky thing to be careful about is n times m is too big. So I have these different sets and maps in order to handle that without inserting every single cell into my data structures. Okay, last problem, problem F. So this one was kind of funny. I don't actually have a proof for this, but my thinking for this problem was kind of like this. Basically, I claimed that you're not going to actually use the reflection to make things congruent. You're only going to use, or even translation, you're only going to use rotation. And you're only going to use rotation around the very center of the grid. So if this is the center of the grid, your path can look something like this. And then we're going to make it symmetric, right? You can go out there. And then you can go, up, up here, and then up again. Whoops. And then what did I do? Did I make that symmetric? Yeah, it looks like I did. Okay, so this is the center. And notice that if you rotate everything around that center 180 degrees, it ends up the same thing. And you need to reach an edge of the grid at the end. So I guess actually we would have to pretend this grid is a little bit wider, because otherwise we already reached the edge here. But we're saying we're reaching the top edge here. And then the cost is the number of pairs that cross this. So it's the number of pairs that are here and also here. And the number of pairs that cross this edge, and so on. You're just adding the number of pairs that cross each of the edges you take. And so when we read the input, we're actually saying that this pair adds one cost to this edge. And then we're just finding the shortest path from the center to any edge of the grid, keeping in mind that we have to make this thing rotationally symmetric like this. So we have to like mimic, kind of like in this example, we have to mimic the direction we go on one side, on the other side. And we have to add the cost for those. So again, this is just a shortest path algorithm. I just did Dijkstra. And what I do is I read the input pairs, and then I find the edge for that pair. And then I add one to that cost. And then what I make sure to do is for each edge, I take its cost and I also add the cost of the rotationally opposite edge. So this edge corresponds to this edge right here, because if you rotate it around the center, they would map to each other. And so you want to add their costs together, and that way you ensure that you're doing a rotationally symmetric path. Yeah, but otherwise it's just a relatively standard dice draw. You're just gonna dice draw from the center of the grid, and then find the closest thing on any of the edges of the grid. Yeah, and then because we're actually trying to keep the most things, we're trying to output how many things we keep instead of how many things we remove. It's just n minus the dice draw answer. Yeah, so that's F. That's it for this contest. Looks like we still have 6 minutes left, so we'll see how quickly I can upload this. But thanks for checking out this one, and I'll see you in the next video.